The total field scattered field, or TFSF source, injects a plane wave with finite span and separates the computation region into two regions. Inside the source region, both incident and scattered fields are present, and outside, only scattered fields are present. The total field scattered field source works by subtracting at its boundaries any light which is directly transmitted through the source region or reflected from a flat substrate, so that only light that is scattered by a feature contained completely inside the source region will pass through the boundaries and propagate outside to the scattered field region. To get a better idea of how the source works, it's useful to consider what happens in the simple case when the source is injected in free space with no scattering objects, as shown in this movie. The plane wave is injected from one side of the source region and subtracted at the other side. Since there is no scattering, the fields are zero outside of the source boundaries. When there is a substrate, any light which is directly reflected or transmitted through the substrate gets subtracted at the boundaries. The source is able to determine what portion of the fields correspond to directly transmitted and reflected light by using one edge of the source as a reference edge, illustrated by the yellow line in the image here. The refractive index profile of the structure along this edge is measured, and the fields that would be directly reflected or transmitted by the reference refractive index profile can be calculated. This is what gets subtracted at the boundaries during the simulation. Since the refractive index profile at the reference edge is important for this calculation, the side edges of the source should always pass through the substrate and not intersect with the scattering particle. Since the total field scattered field source injects a plane wave over a finite span, the default normalization method, where the transmission result from the monitors is normalized by the amount of power injected by the source, leads to arbitrary values. Because the power injected by the source depends on the size of the plane wave injected in the total field region of the source, it's usually more physically meaningful to normalize transmission results by the source intensity, and this is also known as cross-section units. Cross-section units are usually used in scattering simulations to get the absorption, scattering, and extinction cross-sections. There's a discussion about the different possible normalization methods when using the total field scattered field source, linked below. The total field scattered field source works with absorbing materials and anisotropic materials, and it works with multi-layered substrates. It can also be used to simulate standalone scattering objects or periodic structures in conjunction with periodic or block periodic boundary conditions. Here are some examples to illustrate some of the rules for setting up total field scattered field sources. If using PML boundaries at the sides to simulate a single standalone scatterer, the source should not extend into the PML boundaries at the sides. If simulating a periodic structure, the source can extend through periodic boundaries. If there is a substrate, the source injection axis should be perpendicular to the substrate. If there is a substrate, the edges of the source should intersect with the substrate. The source should not intersect with the scattering object. Some applications which use the total field scattered field source are scattering and defect detection. The total field scattered field source is useful when you want to be able to separate the scattered fields from the total fields and perform analysis on the scattered fields only, such as by getting the scattering cross-section or the angular distribution of scattered light in the far field. In the next unit, we'll set up a total field scattered field source to measure the scattered fields from a particle which represents a defect on a structure.